In this video, we're going to continue and complete our discussion of Cool's operational semantics. We'll be taking a look at the two most complex operations in Cool, the allocation of a new object and dynamic dispatch. We'll begin by giving an informal discussion of what happens when a new object is allocated in Cool. So the first thing that has to happen is we have to allocate space for the object, and essentially that means having enough space for the object's attributes. So we're going to have to allocate a location for every attribute of the object of class T if what we're doing is allocating a new T object. Then we're going to set the attributes of that object to their default values, and in a few minutes we'll say what the default values are and why we need to set the attributes to defaults. And then we evaluate the initializers. So every attribute in the class declaration can have an initializing expression, and we're going to evaluate those and set the resulting attribute values. And then we return the newly allocated object. So these are the steps that are involved in setting up a new object. And as you can see, it's actually more than just allocating a little bit of memory. It's actually quite a bit of computation going on in allocating new objects in Cool. Every class has a default value associated with that class. So for integers, the default value is 0. For booleans, the default value is the boolean false. And for strings, the default value is the empty string. And then for any other class that isn't one of these three basic classes, for any other class, the default value is void. In the operational rules, we're going to need a way to refer to the attributes of a class. So we're going to define a function called class that takes a class name and returns the list of attributes of that class. So here we have all the attributes of class A. Let's say they're A1 through AN. And in addition, this function is also going to tell us for each attribute the declared type of the attribute and the expression that initializes the attribute. And one other important feature of this list is that it includes all the attributes of class A, including the inherited ones. And there's another detail, which is in what order these attributes appear. And this will actually become important when we define the semantics of how attributes are initialized. And the rule is that attributes are listed in greatest ancestor first order. Okay, what do I mean by that? Let's say that we have three classes, A, B, and C. And B inherits from A, and C inherits from B. Okay, and let's say that A defines two attributes, A1 and A2, and B defines two attributes, B1, B2, and C defines two attributes, C1 and C2. Then class of C will list the attributes in the following order. First will come A1 and then A2, because A is the greatest ancestor. Okay, it's the closest to the root of the object hierarchy. And the attributes within class A, or within any class, are always listed in the order in which they textually appear. So first comes A1 and A2. And of course, the type and the initializer are also listed here for both of these attributes, but we're just concentrating here on the order in which the information appears. So then next would come class B. So the attributes of class B would be next. And of course, there would be the type and initializer for those attributes. And then finally, the attributes of class C, again, in the order in which they're listed in the class definition. Okay, so that defines the order of the attributes for any class. It's always in the order from greatest ancestor down the inheritance chain to the class itself, that is the argument of the class function. At this point, we're ready to actually define the formal semantics of new T. And let me switch colors here. So we're going to be allocating a new object of type T, and it's going to be in a context with self-object S0, environment E, and store S. And the first thing we have to do is we have to figure out what kind of object it is that we're actually going to allocate. And the only question is whether T is self-type or not. Because remember, self-type is not the name of an actual class. If T is not self-type, then the class that we're going to allocate is actually a T. T is actually a class name, and that's the kind of object we're going to allocate. If T is self-type, then the kind of object we're going to be allocating is whatever the class is of the self object. So we're going to look at the dynamic type here of the self object, call that X, and that will be the class that we create. That'll be the kind of object that we create. All right, so there's two possibilities. Either allocating an object of type T if T is actually a class name. Otherwise, it's an object of the same dynamic type as the self object. All right, so now we go and look up what kind of object T0 is. All right, and we get out the list of attributes, types, and initializers for T0. So this tells us what we have to do to construct an object of this type. All right, the next thing we do is we allocate locations for each of the attributes. So because there were n attributes, we're going to allocate n locations, one for each attribute. All right, and then we're going to create an object with the class tag T0, and the attributes are going to be bound to these new locations. So the ith attribute will be bound to the ith new location that we just allocated. And then we're going to update the store. Okay, so we're going to take our initial store. Notice that this is the same as the store that we started with. We're going to take S, and we're going to update it so that at these new locations, those locations hold the default values for the types of each of the attributes. Okay, and that gives us the store S1. And now we have to evaluate the initializers, right? To actually initialize the attributes. And we have to think about what the environment is in which those attributes are initialized. And remember, the rule is that within an initializer of an attribute, all the attributes of the class are in scope. All right, so the environment, in this case, for the initializers, will just consist of the attributes, themselves. Okay, so these are the attribute names, and the ith attribute is bound to the ith new memory location, holding the default value initially of that attribute. All right, and then finally, to evaluate the initializers, we just evaluate them as a block in the order in which they appeared in the class function. And this is why it was important to specify the order in the class function. So remember that these attributes include all the inherited attributes. So we'll start by evaluating initializing attributes of the greatest ancestor and working our way down to the attributes declared within the class itself. Notice that the environment here, which has all the attributes in scope, this is an interesting point, this environment has nothing to do with the environment in which new T is actually evaluated. You know, these environments, E and E prime, are completely separate. Okay, so E prime has in scope the names of the attributes of the class. E is some other environment. There's some function somewhere that's calling new T, and the variables that are in scope there are just completely different. Okay, but anyway, evaluating this block of initializers will yield some value, and a new store, the value isn't used for anything. Okay. But the new store is the final store. That's the store that we get out as a result of allocating the object. And then what is the result of new T? Well, it is the new object itself, V. To summarize the semantics of new, notice that the first three steps allocate the object. Those are things that actually allocate the memory for the object. And then in the remaining steps, initialize the object by evaluating a sequence of assignments. And the most important thing probably to understand about initialization, or one of the most important things, is the context in which, or the state in which the initializers are evaluated. So notice that only the attributes are in scope. We emphasize that. And it's the same rule as in typing. So when you're type checking a class declaration, only the attributes are in scope of the, for the initializers of the class. And then that's naturally the same thing that we use when we actually evaluate the initializers at runtime. And the initial values of the attributes are the default values. And we need the defaults precisely because the attributes are in scope inside their own initializers. So it could be, for example, it's perfectly reasonable and cool to have an initializer, let's say like this, and I'm going to leave out all the types here just to save time. But I can assign an attribute A the value of A, and this is perfectly okay because the right-hand side of the initializer has all the attributes in scope. And for this to make sense, A has to have some kind of default value, has to have some initial value. Because I might read it before I might read an attribute before I've actually finished computing its initializer. All right, and the last point here is that notice that in the initialization or in the initialization of an object, self is the object itself is the self object. And what do I mean by that? I forgot to mention this on the previous slide. Just flipping back to that slide for a moment, notice here that in the evaluation of the initializers, what is the context? The self object is V. The self object is V. This is the new object that we have just constructed. And so it's perfectly fine for E1 through En, the initialization expressions over here, to refer to self. And what they will refer to, if they use self, is the object that is being initialized. All right, returning to this, to our summary, it might be a little bit of a surprise how complicated the semantics of new is in Cool. And it's not just Cool that has that property. In fact, every object-oriented language has fairly complex semantics for the initialization of new objects. And it's a combination of features like inheritance and the ability of initializers to refer to the attributes that leads to this kind of complexity. Now let's talk about the semantics of dynamic dispatch, and we'll follow the same plan that we did with the semantics of new. First, I'll have an informal discussion, high-level description of how the evaluation of a dynamic dispatch works, and then we'll look at the formal operational rule. So the first thing that happens in evaluating a dispatch is that we'll evaluate the arguments, E1 through En, and next we'll evaluate the target object, E0. So we'll evaluate that expression to get the actual object to which we're dispatching. Next, we're going to look at the dynamic type of the target object. So after we evaluate E0, we're going to look at what its class tag is. And then we're going to use that type to figure out which function f we're supposed to use. So we're going to go and look in the method table for the class x and see what method it has for f. Then we're going to create new locations and an environment for the call. Okay, so we're going to set up n new locations for the actual parameters. We're going to initialize those locations with the actual arguments. We're going to set self to be the target object, and then we're going to evaluate the body of f. Now, in order to do the lookup of a method in a class, we're going to need some representation of what methods exist in which classes in our operational rules. So we're going to define a function impl, stands for implementation, and the implementation in a class A of a method f is going to be, first of all, the list of formal parameters. So it's going to tell us what the formal parameters are of f, and then the body of f, whatever the function body of f is. Now we're ready to actually discuss the details of the formal operational semantics of method dispatch in Cool. And I'm going to switch colors here, again, just for contrast. So as we said, the first thing we do is we evaluate the n arguments. So these first n lines take care of that. And notice that each argument that's evaluated may have side effects. So it starts in some store, but it may produce a different store. So after we've done all of this, we have the n arguments evaluated and some store s sub n. The next thing that happens is we evaluate E0. This is the expression to which we are dispatching. And that will give us an object V0 and some updated store s sub n plus 1. Okay, and now we have to inspect V0. We want to know what's inside of V0 or what V0 is made of. And in particular, we're interested in the class tag of v0, and we'll also be interested in the contents of its attributes, the locations associated with its attributes. But first, let's focus on the class tag, all right, because we're going to use that class. Remember, this is the dynamic type of v0. This is what kind of object v0 actually is when the program is running. And we're going to use that class to look up the definition of f that we should run. So we look for the method f in class X. We want to know its implementation. And in particular, we get the names of the formal parameters, okay, x1 through xn, and we get the body of the function or method. All right, so the next thing we have to do is we have to allocate space in the memory or in the store for the actual parameters of the method call. So we allocate n new locations, okay, one for each actual argument. And now we're ready to build an environment in which we can evaluate the method. All right, so what is this environment going to consist of? So we have to think about what names are in scope inside of a method. Well, all the attributes of the class are in scope. Okay, so this is a class X with attributes A1 through AM. So the environment will have those names defined, A1 through AM. And now what are the actual locations of those attributes? Well, those are the locations of v0. That's the object that we're dispatching to. That's going to be the self object. And the attribute names will refer to the attributes of self. All right, so the locations here are the locations of the attributes in the object v0. Now, in addition, the formal parameters are also in scope inside of the method body. So we add to this environment with just the attributes all of the formal parameters. Okay? And they are at the new locations L sub x1 up to L sub xn. Okay? And notice, though, one slight subtlety about the way this is defined. We're taking an initial environment, which I'll show here with, I'll color these braces in blue. So we're defining initial environment of the attributes, and then we're doing updates to that. Okay, so and instead of just defining x1 to map to L sub x1, we're saying we're replacing the definition of x1 in this environment in the blue braces with one that maps x1 to L of x1. And why do we do it that way? Well, the thing is that a method may have a formal parameter that is the same as an attribute name. So for example, I could have a class A that has an attribute little a in it, and it also has a method f that takes a formal parameter named a. Okay, and if I do that, and of course I'm leaving out types and lots of other things here. So here I have an attribute named a that's declared, and then I have a method that takes an argument called a. And now the question is, when I refer to a inside of the body of the method, what a do I get? Does this a bind to the formal parameter, or does it bind to the attribute? And the answer, we have to give one answer or the other. The answer in cool is that it binds to the formal parameter. That hides the outer name. Okay, and that's enforced here in the rule by these updates. So if a formal parameter has the same name as one of the attributes, it will replace the definition of the attribute in the environment. Okay, once we have the environment set up, we need to set up our store. What are the changes to the store? Well, we just have to store the actual value of each argument at the location for that argument. And finally, we're ready to evaluate the function body. And the interesting part here is the context in which that's done. So notice here that the self object in the context of running the method f is the object to which we're dispatching. Okay, and then the environment is e prime, in the new environment we just set up. And once again, notice that this is a complete change of context. That e prime, the environment e prime, has nothing to do with the environment e. E prime is built completely from scratch using only information about the method we're calling. It doesn't borrow anything from the environment where the method originated, where the method was called from. And finally, all of this is done in the store that reflects all the side effects performed by evaluating the arguments, by evaluating E0, and by extending the store with locations for the actual parameters. So we evaluate the body of the method, we get back a value and another updated store, and that value and store are the result of the entire execution of the dynamic dispatch.